So hello, everyone. Hey, this session will be starting in just a couple minutes. We'll give people time to join, and we'll give it a minute or two, and then we'll get started. Okay, everybody. I think we'll get started. So, want to say hello to everyone. Thanks for joining us, and again, thanks for your interest in JMAG. And so, my name is Brian Kowalczyk from PowerSys, and I wanted to welcome you to this session about efficient motor drive development and validation. So in this session, you're going to see a presentation from PowerSys and followed by a presentation from PowerSim. So first, we'll hear from my colleague, Dheeraj Baba. He's one of our JMAG technical experts at PowerSys. Dheeraj is currently a senior electromagnetic design engineer at PowerSys Solutions. He's held positions as applications and project engineer focusing on low frequency electromagnetics in the past. He obtained his PhD, master's, and bachelor's, all in electrical engineering. His current research interests include high power density electric machine design, control, and optimization techniques focusing on traction and aerospace applications. So with that, I want to welcome Dheeraj to share his presentation. So take it away, Dheeraj.
Awesome. Thank you, Brian, and hope you can see my screen here. Let me start off with
we can see it.
Sure, sounds good. So let me start with a little bit of introduction for this session. Of course, the session title is Efficient Motor Drive Development and Validation. As Brian explained, there will be 3 speakers in this session. The first, I will give the introduction for the rest of the 2. To give an overview, this is the looking at the workflow in a machine design and development. So there's different aspects of this covering different tools. So I will be covering the initial machine design phase and how to lay the outline for connecting with the rest of the parts. And the second part of the presentation will be from PSIM, which will be machine and drive validation. And the last one will be from Typhoon Hill, which will be looking at the hardware envelope simulation. So the outline for this presentation will be introduction of JMAG toolchain and more focusing on JMAG RT and some demo for generating JMAG RT models, and talking about some advantages of using JMAG RT and maybe some other ways to use the RT block itself or RT generated data within JMAG. And lastly, with some application examples of JMAG RT. So let me start with the JMAG toolchain introduction. Ideally, when you're designing a machine, you would start with some analytical 1D models or calculations that will give you a rough size of the machine. In JMAG, you can do the concept level design using JMAG Express. Of course, that's entirely focused on machines. And then there's transformer template tool that can also be used to generate simple transformer templates. This is more in the realm of initial sizing and quick parametric analysis. And you can also connect or export the models from this template tool and JMAG Express into JMAG Designer, which will be focused on a more detailed design. This is where you can also import your custom CAD models and apply all the electromagnetic analysis, electrostatic, structural, and thermal analysis conditions to the model and run those studies. And it also includes an optimization toolbox if you want to run parametric or performance optimization. And then the next step would be to take these models into system level analysis or even one-dimensional analysis. This is where JMAG RT comes in. Of course, there's a way to directly link FEA models from JMAG Designer into a system level analysis as well. But RT is more focused on control circuit or one-dimensional simulations that run at a much faster pace. And of course, hardware in the loop simulations also fall within the same realm. So we'll be, for this rest of the presentation, I'll be focusing more on JMAG RT and its advantages. So first, let's start with the question of what is JMAG RT? Basically, it is a tool that uses model data that's running the FEA model at several operating points, collecting all the data into lookup tables and generates a kind of a black box model, a one-dimensional model that takes in the operating point input and gives you the performance for that operating point. So all the process to generate the operating points, generate the results, and packaging that into the block is handled automatically by JMAG RT interface, and it has some limited user input required. And there are two models available within JMAG RT. One is the simple lump parameter model that, of course, includes saturation impacts, but this is more for a quick analysis. And then there is a full spatial harmonic model for high-fidelity modeling. There are multiple ways to generate this JMAG RT model or the JMAG RT block, and I'll be going through the demo of each of these. But basically, from the JMAG Express, from the template tool, you can simply generate JMAG RT, which is a simple LDLK model with impact saturation on it. And then from JMAG Designer, we can use the full FEA model to either 2D or 3D and generate the block. And also you can import CSV files from actual experimental data and incorporate that into the JMAG RT model. The last way would be using our predefined motor library that's available on JMAG website. So to go through the demo, the first one is JMAG Express. Here I just have the interface open, and it's very simple. Simply go and click on that JMAG RT block, specify a path for the output file, and click OK. And it'll take a few seconds, and the JMAG RT model is created. You should be able to export that into your control circuit simulation. And the next one is using the JMAG RT Maker or the RT interface. And this is basically using a model that was developed or created in JMAG Designer for full FEA. So the process is simply click on New. There's different types of motors, so you pick the right type of machine that you're working on. RT here, it's a PM machine. It can be 3 or 6 phase. And as I said, there's LDLK model or spatial harmonic model. And this is where you can also import the CSV file from experimental data. I'll use the spatial harmonic model here. Click OK, give it a title. This is an IPM machine. And then go to the Create tab and give some basic information such as the number of poles, number of turns, and the phase resistance. I'll use the auto setting for current information, basically give the rated current value. Click OK, and everything else is set up automatically. Click OK, and then simply run the model, and this will generate RT file. This will take a little while because it has to run through all the operating points and collect all the data. So I will not keep it running all the while, but I'll pause it here. But at the end of it, this will generate the RT file that can be incorporated. Then the last one, as I said, is using the JMAG website or the RT model library. You can go to the library that's available at this link, the technical library, RT model library, and there's quite a few types of machines available here. Just scrolling through. This SPM, IPM, and machine. So we'll go and pick one machine here, and all the machine information is available here. You can create an account, and you should be able to download the RT file from this link. So with all that information, now the bigger question now is, why should we use JMAG RT? There are already motor blocks available in control circuit simulators. So for example, this is a motor block from PSIM, and it has all the information that we can enter, like the phase resistance, inductances, and some mechanical constants for the machine characteristics. And typically, information is being used in this lump parameter model that is shown by this D and Q axis circuits. And the torque can be calculated with something looks like this. And if we plot the current versus torque response, it's usually linear because all these values are constant. As the current increases, which is ID and IQ, the torque goes up. But in reality, the inductances are variable, meaning as saturation increases, the inductance decreases. And this can also be captured using lookup tables for D and Q axis inductances. And if you plot the current response for the torque response for the current here, there'll be slight deviation. As current increases, inductance goes down based on this table, and the torque goes down. Well then, what's next on that? So the PM flux linkage can also be dependent on saturation level. Usually that's not something we give as a table for lump parameter models. In addition to that, the inductances are also dependent on the rotor position, and there are more components in the inductance, the DQ mutual coupling and the zero sequence inductance. So these are all the aspects that are covered or completely captured in a full spatial harmonic model, which includes nonlinearities. And of course, in this model, the torque is directly from FEA, so the fidelity will be much higher as well. So if we plot the torque response, in this case, we can see that deviates further from the constant LD-LQ model and the LD-LQ table model. So that way, that's where the spatial harmonic model has a higher advantage in capturing with higher fidelity. And in addition to that, if you look at the transient or a time response of the torque, the controller must be tuned more precisely to capture the transients. So in this case, I plotted the torque with a DQ table. That's the blue line, and the orange line here is the spatial harmonic model. So the controller is more tuned for the spatial harmonic, but if you run the DQ model, there's a huge spike. And the inverse is also true in the sense that if you're using a lookup table model and the controller is tuned for that, the PI gains are tuned for that, then that would not handle spatial harmonic or the actual machine's transient response. In addition, if we zoom in on the steady state operation, since the inductance is rotor position dependent, that information is captured in the spatial harmonic model, and we can see the complete torque ripple showing up, while that response is not shown in the table model because the inductance is constant, the torque is constant. So these are some of the aspects that we have to keep in mind when we're choosing which type of motor model we want to use in circuit simulation or control design. There's a few more benefits that I've listed here. One of the key ones is that the JMAG RT block is stored independent of the source model, and it only contains the numerical information. That leads to a faster processing speed while retaining the full fidelity from FEA. And in addition, the iron loss data can also be incorporated. And while this RT block is being used in a system level analysis, this iron loss data can also be incorporated into that. Also, the motor model and the high fidelity performance data can be shared with other teams, be it within the company or even a third-party vendor, without disclosing the machine geometry, because the RT block contains all the performance information in raw data form. It does not have any geometry information. And finally, the same fidelity and the streamlined performance data can be maintained starting from the machine design all the way to the control unit validation. And this enables identifying potential system level issues at the early stage and fine-tuning the performance. And by no means this is an exhaustive list. There's many more benefits that can be listed out. But next, let's move on to what can we do with the JMAG RT. So first I'll cover within JMAG toolchain and then we'll look at some examples that are outside JMAG, or in a sense, using the RT in general. So the first one is JMAG RT Viewer. This is something that's available along with JMAG Designer. We can import the RT file into this RT Viewer and set up some system characteristics like the DC bus, the switching voltage, so the switching frequency, max speed, max current, and pick a basic control type, or even give a detailed control algorithm, and we should be able to generate some of the performance metrics. First, here are some examples with the RT file: torque speed curve, the DQ plane torque map, similarly LD and LQ inductance maps, the efficiency map, and also iron loss map. So this is for a quick visual check of what the motor is or what the performance is without going into elaborate control design. And then if you have tuned into the presentation earlier today from my colleague Simon, she pointed out to the JMAG RT-FVS switch. So this is something that can help in terms of applying the control circuit and trying to figure out the transient response of the machine in FVA to, let's say, to look at magnet eddy current losses. So this has multiple blocks here. There's a JMAG RT block that's identified in blue. And then we have the actual FVA model, and there's a switch in between that switches from RT simulation to FVA simulation when it detects that the system is in steady state. The results would look something like this. So the orange waveform in the back is a simulation using full FVA, which goes through the transient for the full 0.1 second. And the second one in blue is the RT model switch is being used. So it will quickly determine the steady state and start the FEA analysis from the steady state operating point. This will reduce a lot of analysis time to go through that entire transient. Now moving on to some examples. The first one is something that we have worked and recently published. This is basically dealing with a hybrid rotor PM machine that has multiple rotor segments on it. And due to its nature, it requires 3D modeling usually. What we did is we took 2D cross sections of each rotor type, created JMAG RT models, and combined them. And with that, instead of 2 hours, the single operating point went down to 0.4 seconds. And comparing the results, it holds the full fidelity of the full FEA. So this is the voltage and the torque waveform along with the torque ripple. And the second one is an example from a presentation made by Honda at JMAG user conference in 2020. And this is basically, they identified some controllability issues at some operating range. And this actually covers two aspects. They were able to share the RT file with an outside supplier, and they were able to figure out the cause of that controllability issue and come up with an alternative modulation method to suppress that. And this was caught on much earlier stage and were able to reduce the design cycle time. And the last one is also from a JMAG user conference in 2019 by Toyota. And this covers a similar scenario where they identified some resonance in the system, and they came up with a better control scheme with square wave modulation instead of the PWM to essentially reduce the resonance in the system. And again, there's a lot more examples that are available on the JMAG website. I've shown some links here at the bottom. So you can go to the technical library and user conference proceedings or the application catalog to look into more details. With that, we are right about on time. So I will introduce our next speaker, Dr. Hua Jin. He received the bachelor's degree from Yunnan University, China in 1984. And master's and PhD degrees from University of Toronto, Canada in 1987 and 1991, all in electrical engineering. From 91 to 99, he worked at Concordia University and the University of British Columbia, Canada as a professor engaging in teaching and research in power electronics and motor drives. He was the developer of PSIM software, and he founded PSIM Inc. in 2001, and he's currently the president of the company. So with that, I will hand over the ball to Dr. Hua Jin.
Hello, can you hear me?
Yes, we can. let
Oh, hi.
me-
Yes, Daraj, thank you very much for the introduction.
This is Brian. I'm going to take care of hosting. Hua.
Oops.
Where did Hua go? Looks like we might have lost Hua. We'll give him a second to rejoin.
Yep, while we wait for Wajin to rejoin, feel free to post any questions if you have, and we'll be happy to answer.
So Dheeraj, this is Brian. We do have a question for you for RT. Does JMAG RT handle transient iron loss and copper AC loss?
There is a way to include the transient iron loss in the simulation in the control circuit, but I think the other part is something that's upcoming in the next version. The AC loss is not in the current version.
Okay, thank you. Dheeraj, I have another question for you.
Mm-hmm.
Is the 6-phase version of RT file creation available in future version? I couldn't see it in the current version.
No, there is a 6-phase RT. 6-phase is supported in the current version. We should be able to create a 6-phase machine. In fact, there's also a generic motor block that can, it is possible to use the current version to do that.
Okay. Another one is JMAG RT included with JMAG Designer, or is it an add-on?
It is a add-on on the license, but it is available. It is available as an installation package, but the license is an add-on.
Mm-hmm.